So Benjamin just gave you an overview about what all things we are doing at the product level in terms of improving the performance, whether that's parallel processing, adaptive SQL plan. We thought that we'll also show, or let's say discuss, one of the use case that we were involved with, and which was basically real-time analytics and high-performance ingestion. So this session is more like a use case as opposed to from a product level. So the use case that we had was basically, it's a financial use case where essentially you have lot much of streaming data which needs to be persisted into the database at high volume, speed, velocity, whatever you want to call it, and at the same time process that data using SQL queries and make it available at an application or an API level through REST interfaces. So essentially, we are inserting lots amounts of data, but at the same time, querying the same data in real time to look at the data in a different way. So the data might be raw, like a ticker data or a stock trading data, but what they want to look at is what is the highest value, what is the low value, average value. So compute some kind of aggregates around that. But more importantly, make that data easily available via REST API by any application. So the prospect in this case has many customers who have their applications written and they just subscribe to these APIs and they have access to this processed information in real time. So what are the challenges when we look at a use case like this? So the prospect basically came to us is basically with a target of saying, we need to ingest roughly 1 million records a second and at the same time do thousands of REST APIs per second on that volume of data in real time for their in-day processing. So they had two use cases. One is a historical processing use case where they might have billions and billions of records, but over there, the query volumes are not so large. But in this particular use case, you're looking at an in-day processing of data in real time, and there are thousands of people who are accessing that data. And when I say 1,000 REST API, each REST API behind the scenes is actually doing 5 to 6 SQLs to construct the payload which needs to be generated for the output that REST API provides. So essentially, when I say 1,000 REST APIs per second, essentially what they meant was 5,000 SQLs per second, basically. Now, obviously, how do you do this? People have tried with in-memory databases, but the challenge is they're very, let's say, expensive. And if something happens, then everybody knows it takes a lot of time to recover from those failures. The other thing, which is probably a cloud paradigm, which is basically you have different databases for different workloads. You might have one service in a particular cloud vendor for ingesting data, and they might have another service which they're using for querying the same data. But the challenge with that approach is essentially that they very easily at that scale run into synchronization issues, because essentially what they're querying is they're trying to cache the data, but to keep that caching layer in sync with the database layer where they're actually ingesting the data is not, again, an easy problem to solve. And more importantly, when you're querying in real time beyond a certain scale, even to keep the indexes updated in real time, again, becomes an interesting challenge. So these were the issues that they had, and they came to us and say, okay, can you demonstrate that how would you use Iris as a data platform? And Benjamin talked about our ECP infrastructure, and the key thing in this case was that we said, okay, what we will do is we'll exactly show you how that architecture is going to look like. So what we did was we got 1 day's worth of data, which was lots of GBs of information, I would say, loaded on through S3 files in AWS. We basically did one thing was that, again, when you're doing something like this, I guess I would have spent 80% of my time in building all the infrastructure which didn't include Iris. let's say. Because when you're trying to demonstrate something like this, you need something which can throw data at that rate onto Iris. So what we did was that we built this entire POC in AWS. We spun up managed Kafka cluster with 3 brokers and 100 partitions in AWS. And we basically, what we did was, whatever data that they had provided us in the object storage, we loaded that data into that Kafka cluster so that it can stream data at huge volumes into Iris. The other bit that we have now, I think so, I don't know, Jeff, whether it's the next version or the 2023 version, is a new Iris persister high-speed ingestion component that we have added to our database capabilities, where essentially it's a multi-threaded program written currently in Java, could be .NET in future as well, which is essentially reading the data from these Kafka streams and in a multi-threaded environment trying to persist the data into Iris as a database. And if you look at it, what we put together for this is a database node, and what Benjamin was explaining, 3 compute nodes, which in this case were actually query nodes, where actually the REST API was residing. And again, as Benjamin was saying, our ECP infrastructure is completely transparent. So whether you run this REST service over here or you run in a horizontally scaled ECP infrastructure, it's one and the same thing. But the key thing over here is that we are only using the database node for the ingestion traffic, but all the query traffic is being moved onto the ECP nodes, which is actually where the REST API is getting executed and actually is where the data is being serviced through a load balancer, which gave to another problem that we had to find was, okay, now we need a harness which can generate those many REST APIs per second, because we had to do thousands of REST APIs per second. And we looked at and we came up with JMeter, which is an open source REST client from Apache, where essentially we configured it on 3 different nodes on AWS and make it send lots of REST APIs to an application load balancer, which was further load balancing in a round-robin manner to the 3 ECP servers connected to a single DB node. So entirety, if I were to look at the infrastructure that we put for this particular POC, was basically sample data we had in S3 objects. We wrote a program to load those S3 files in JSON format into a Apache cluster. Then from those Apache cluster, we basically wrote a program utilizing our Iris persister component to ingest the data into Iris. And the REST API, which was a bunch of SQL commands for a particular API, was running on each of these ECP servers. So from an Iris perspective, I would say the beauty of it was that, I think so the work that I did in Iris was probably 1 day, because it included a very simple schema of 7 to 8 tables and a REST API trying to access data through those tables and being able to run that on an ECP node, which just needs a remote database connection to my database node. But all the infrastructure else that we had to work, I guess, took me days and days and weeks, I would say. So just an idea around what basically we did was, so just the architecture in terms of how the Iris persister works, from a Kafka cluster to be able to write a multi-threaded Java program, which can actually consume data from Kafka cluster partitions, and then actually, again, have a multi-threaded program to ingest the data into Iris. Again, this is not using JDBC, this is using our Iris native APIs, which are as fast as they can be. So the idea was to basically do that in the most high performance manner, because that's what the requirement was. I mean, this is just showing how an Iris persister works. And the other thing about Iris persister is that it is written in a way that either you can create the schema within this Iris persister, or it could synchronize it from the server. So it gives you a complete flexibility in terms of how you want your database schema to be. It could read it from a file, it could be anything. or if it already exists on the server, that means Iris server, it could synchronize it from there. And I think so this is what Benjamin was explaining, where essentially we had 3 ECP nodes over connected to a single database node, which allowed us to scale horizontally. Okay, let's look at how that actually looks like. So I have 4 windows basically open here. I think the sessions might have timed out. If I'm lucky, they're not. So that should take less time. Oh, they're not. So this is a session which basically is a session which is basically connecting to the DB node. And these are the 3 sessions which are basically where I'm running the harness, which are generating the REST APIs at whatever rate we have configured. It's currently basically using 30 symbols per REST API, which means roughly 150 SQLs per message that we are trying to inject. And we have 3 JMeter nodes, which are basically sending the information. So this is when I'm starting the ingestion, and this is when I'm starting the JMeter nodes, which are actually querying the data. Okay, so I have 4 nodes now, actually 3 nodes which are basically the query nodes, and essentially there's 1 database node which is actually ingesting data, and then you will, it ramps up and you will see it will be roughly stabilizing around 1 million messages per second. But the interesting thing is basically when we see this as million messages per second, the reality is that we could do much more than that, because essentially our CPU utilization on the database node does not go more than 40%, even with billion messages per second. But where we are bottlenecked by is the storage. How fast is the storage in terms of IOPS and everything? And the other thing to look at from that perspective is that the more faster storage that you need, the more expensive it starts becoming. And I think so that's a key consideration that needs to be kept into the mind. So if I go to these 3 query nodes, okay, and I go to the database node, let's look at the CPU utilization in the last 5 seconds. AWS takes some time, I think so. So you will see some of the, I would say, the JMeter nodes or the query nodes are already going up to 60%. And what we found was, which is what we thought actually, that essentially what we want is you will have a database node plateau beyond a point, because essentially that's the maximum CPU which we can utilize based on the storage which we had. So around 1 million messages per second, we were using roughly 40 to 50% of the CPU. But on each of the ECP nodes, we were hitting roughly 60 to 70 or 80% of CPU, which is that means we are maxing out CPU on the query nodes, and that's exactly what we need. Because if we are trying to horizontally scale the query workload, then essentially what we want that we are making the maximum utilization of these ECP nodes for the query traffic. And the key thing is also is that the ECP layer can be completely elastic, because essentially at your load balancer using the cloud, I would say what cloud allows you to do is easily add another ECP node on demand based on the incoming traffic or the CPU utilization across all the other nodes that you might have. So you can see we are almost reaching 80% on those nodes in terms of the CPU traffic. So essentially, I think so. We get asked this a lot sometimes, because even on our website, when we say concurrent transaction and analytics, what does that mean in terms of Iris? Now, in this case, we are scaling the compute. So we're not scaling the data in the sense we're not distributing the data. The data still resides in tables which are not sharded on a single DB node, but it's the query volume, which is what this prospect needed, because they wanted this scalability across the query volume, across large amounts of data, which they basically process for their in-day processing. And that's what the use case was pretty much. So if you look at it, when we did this, the database node that we were using was roughly 32 cores and 256 gigabytes of memory. I don't think so we needed that much kind of memory, but the reality is in the cloud world, that's how you get those instances. But we needed basically 32 cores on the database node, which again, we are just using 40% of the CPU. But obviously, if we had a better storage, or if we had two, let's say, Iris nodes where we had to ingest the data, then again, we could actually take it further up from that standpoint of view. On each of the REST APIs that we did, so we experimented with number of symbols, because the reality is that these REST APIs are equivalent to portfolios of different high network worth individuals, which are querying for their sets of financial instruments. There could be either 10 symbols in that REST API, or there could be as much as 30 symbols for REST API. And again, the whole idea was to see that, again, we were scaling quite well. So it was not that with 10 symbols or 30, the moment we increased the number of symbols, it had a steep curve down. Because that's the other thing that many of the other databases, you will find that beyond a certain threshold, the performance decreases like anything. Now, in this particular case, obviously, the case that Benjamin has mentioned about the lab test with so many thousands of CPU nodes, obviously, that this is much smaller in that. But this is a real-time use, real-life use case where essentially, I think so, when we asked them, what do you think that probably, if they were to put this in a native cloud paradigm, I think so, the answer was that probably they're looking at around 200 cores of what they would need to build something like that. Whereas what we were trying to do over here was pretty much around 50 cores of Iris, and we could scale to their throughput requirements, both in terms of ingestion and query, with probably 1/4 of the infrastructure that we would need in the cloud environment. So I think it was a very good use case for us, and again, to test for us that how good Iris is in this kind of a scenario. And I think so we came out quite well, but I just wanted to make sure that we share this use case with you as part of this presentation to look at it basically when we talk about concurrent transaction and analytics in real time. We're not talking about analytics on a warehousing environment or anything like that. Here we are talking about the data is getting ingested and you're querying in real time. That's how typically an architecture looks like. And depending on the scale of REST APIs, this could horizontally scale to 5, 6, 7 nodes, as many you want. And similarly on the database node, either you could scale it vertically, depending on how big an instance you want, but if you want to even shard it, you could do that as well. If you wanted to go to, let's say, 4 million inserts per second. And again, I've picked a financial services use case, but this could be for any IoT use case or anything, because the data element itself, each row that we are processing is not big. You're just probably processing 3 to 4 kilobytes of information, not more than that. But the key thing is it's coming at a very high ingestion rate, and what kind of architecture you would put. And the key important thing, I can't stress it enough, that to put something in architecture like this in Iris is pure configuration. Whereas if you go into native cloud paradigms, to spin up a caching node and to synchronize it with the database node, you cannot imagine how difficult that proposition becomes very easily at a certain scale. Thank you very much. Any questions?